Hello everybody, today we're going to be recapping and looking further at vectors. So first of all, we need to just go over a couple of the objectives here. You need to be able to identify the forces in free body diagrams and a variety of vector and forces applications. You need to be able to calculate the size and direction of those angle forces, so the resultant based on their components of the orthogonal directions. You need to be able to label closed vector diagrams, and we'll go into detail a little bit more on that later. And we need to be able to calculate forces acting on objects and slopes using that vector analysis. So first of all, let's quickly recap through. You know, forces are vectors, which means they have magnitude and direction, as opposed to a scalar, which just has a magnitude associated with it. And we're going to couch this in the context of medieval forces. So here's an example, not medieval actually. The wire fence in this bird's eye view. So bird's eye view actually looking down. Here's a fence post as you're looking down from it, and there is a wire getting pulled that way and pulled that way. So imagine you're tightening the wire by pulling it in two separate directions. There's a force that way and a force that way. The net force must be somewhere in between. So there must be a force like going this way, if you follow my cursor, because that's going to be the resultant if you put those two vectors together. So the net force can be found by drawing all of those forces head to tail. And by head to tail, we mean draw the first force and then add the second force on, and then we can complete the triangle using these two arrows here to show the resultant force, or the net force in this case, by drawing from the head or the tail of one arrow to the head of the other one. Individual forces are marked by single arrows, and the net force is marked by double arrows, as I just said. Pretty straightforward. So here's an example here. We've got 310 newtons pulling in this direction from the fence and 120 newtons in that direction. If we want to find the size of that force, we just use Pythagoras as we used before. So we've got 310 squared and 120 squared, using c squared equals a squared plus b squared is equal to the net force squared. So we just take the squared value of that as 110,500, take the square root of that, and we end up with 330. And there's our resultant vector with those two arrows showing it head to tail. And we calculate the net force there. They've just rounded it to two significant figures and they've included the units. Remember to include your units, you do get marks in the exam for that. So the direction of the force then can be found with trig, and you should know if you have an opposite and adjacent side, we're going to use tan using SOHCAHTOA. So tan is equal to opposite over adjacent, so the opposite side, in this case when we're using this angle here, is 310 and the adjacent side is 120, so tan of theta equals 310 over 120, tan of theta equals that, and then we take the inverse of the tan to get the angle. Tan to the -1 of whatever that value is gives us 68.83, and that's just rounded up to two significant figures, which is 69. So that angle there, and it obviously does depend on which angle you're measuring from. If we're measuring from that angle there, then we'd use a different one. We'd use that be the adjacent side and that would be the opposite side, so you just have to make sure you know which is A, O and H for the hypotenuse. So we know the force, we know there's no net force on this object because nothing's moving. From Newton's laws, we know that there's no net force on the object, therefore the object is at rest or it's moving at a steady velocity. In this case, the fence isn't moving at a steady velocity, it's just we've got a force in this direction, we've got a force in this direction, so we know that this fence post isn't moving, so there must be an equal and opposite force in the opposite direction stopping it. In other words, there must be a reaction force balancing these two applied forces on the pole. Now you can get the resultant applied force, which is going to be in that direction as we saw earlier. So there must be an equal and opposite force in the opposite direction, stopping the fence post from moving. When the forces are balanced, we can use what's called a closed vector diagram to display all of the forces and find any of the missing forces then. So closed vector diagrams, we draw all the forces acting on the object head to tail. When the forces are balanced, they will form a triangle or another closed shape. You know, don't always just get two orthogonal forces. You can get all sorts of forces. So whatever the shape happens to be, it has to be closed. In other words, the perimeter has to be whole. And we just use normal arrows for these diagrams. You notice there's no double arrow in here because there's no net force vector. In other words, we're not drawing the resultant force. We're drawing all the separate forces that are balanced, so therefore there's no net force. So we have a force in that direction from the fence post, a force in that direction, which would result in that resultant force, but the force for the support pushing back in the opposite direction is this way. So you can see there's one direction, okay, for this closed vector diagram. It goes round in a complete loop. The missing force in this case here is the support force, which we didn't draw earlier, so therefore that was the missing force. So when we're looking at angles and so forth, calculations often involve angled forces, and you can make those easier by separating the forces into horizontal and vertical components. And I know you touched on this a little bit before. Let's say that we have an angled force here, which is an angle theta from the horizontal. We can resolve this H force here into force A and force O, adjacent and opposite. And we can do that with trig. We've got SOHCAHTOA, haven't we? Sine of theta equals opposite over hypotenuse, and so on and so on. So as long as we know two of them, from theta, O, H, and A, the other two values can be found, because you can just use trig for that. So here's an example. This battering ram, okay, has been pulled back in this direction. Okay, so we're pulling back this battering ram. There's a wire attached to this weight here, and we pulled it back in this direction. So we pulled this wire from vertical to an angle, which is 20 degrees from the vertical, and we're pulling it back in this direction. We're holding it there, so therefore it's at rest. It's just about to be pushed forward, so in this direction, to break down a door. So here's our closed vector diagram. We have the weight pulling down here, which is down there. We have the force applied, which we're pulling back in that direction. So on a closed vector diagram, there must be a tension in this direction here, completing that. That's the missing one here. So we have the weight, we have our force that we're pulling back on the battering ram, and so therefore the closed vector diagram is going to have a tensional force from the wire, keeping it at rest. So what we want to do is we want to calculate the weight force, the applied force, and the tension force on that battering ram. So let's do that. Well, we've got a mass here, so we have to change that to a force to start off with. We use that force equation, F equals ma, to calculate the weight on the ram. So force is equal to 75 times 9.8, or whatever is in your formula and constant sheet for G. And so therefore the weight pulling down, that's the vertical component, is going to be equal to 740 newtons. They rounded that to two significant figures. Remember that 0 doesn't count. It's actually 735, as we'll see in a minute. Now, so we've done the weight, that's good. Now we need to find this other component, the force applied, the applied force on the ram. Okay, so we know that the downward component is 735 to three significant figures. So, excuse me. So what we can do is use trig to calculate the applied force. Okay, we know that tan of theta is equal to opposite over adjacent. Okay, we've got that 20 degrees there. We've got the adjacent side, which we've already worked out. We just need to work out this opposite side. So we've got two of the three variables that we need. Tan of 20, because remember that's 20 from the vertical there. And the reason why they got 20 there and 20 there is just due to the angles that you learn in junior. You know that angle there is the same as that angle there. So tan of 20 is equal to force applied, which we're trying to work out, divided by 735. So just rearranging that equation to find out force applied, you go through all this calculation and we end up with 270 to two significant figures, or if you wanted it to 4 significant, 5 significant figures, there's the value there. So 270. So next we do the tensional force. Excuse me. We can use trig again. Okay, so we've got our triangle here. We know this one, we know this one. We actually only need to use this one here because we can use the cos, which is adjacent over hypotenuse. Again, cos 20 to 735 over the tensional force, which we need to work out. Again, working that all through, we end up with 780 to two significant figures. The only thing you've just got to watch out for is which force is the opposite, which force is the adjacent, and which force is the hypotenuse. And as long as you can work all that out, the maths is pretty straightforward. So applying that to objects on slopes, we have this object on a slope here. The weight force is always straight down. So the weight force points straight down. The force of gravity acts on the object in two ways. Okay, the object is pressed against the surface, so we have a component of the gravity in this direction pushing against the surface, and we have a component down the slope pulling the object down in this direction. It's only the friction stopping it going in that direction. So this is the total weight getting pulled down. We can resolve that into two components, one which is orthogonal to the surface of the slope and one which is parallel to the slope. So these two component forces are now at right angles to each other. So we can basically complete the triangle at this point now. Okay, the object is at rest, and that would be said in the question, which means that that weight force must be opposed. Okay, the force pulling the object into the slope is supported by the support force. So in other words, this pulling down here is supported by, let me just get them both on screen so you can see. We have a force into the slope, okay, and then we have a support force. So if you like a normal force pushing back in that direction, we still have the weight force pushing down this way. And we also have the force pulling the object down the slope as opposed by friction in the opposite direction, and that's this vector here. Okay, so we've got three vectors which we need to resolve. Okay, so we've got these three vectors here. We can rearrange these vectors now to complete the closed vector diagram. So we've got one pulling down here, we've got one pulling down there, that's this one, and we've got one, the support one, pushing up that way. So that's the closed vector diagram. The two components of the force can be found with trig now. Okay, so if we've got the mass of it, we've got 1,000 newtons pulling in this direction. Okay, we've got 20 degrees. Again, you can work out the angle from that. Okay, and so we can use sine and cos to be able to work out these angles. So first of all, the weight of the object is 1,000 newtons. The angle of the slope is 20. So calculate the component that pulls the object down the slope. So this one here, we're looking at this one here, and that's the opposite side. So we can use sine. So the sine of 20, because it's 20 degrees, is the force down the slope. So that's that one there. They could have put F down slope instead. Divided by 1,000, go through all the calculations, you get 340 newtons. So the force pulling the object down the slope, which is that one there, is 340 newtons. Just rounded to two significant figures. So therefore the frictional force must be equal and opposite to that, because it's at rest. That's Newton's laws. Okay? The weight of the object is 1,000 newtons, the angle is 20. So the component that pulls it into, well, you're going to get this, you know that it's going to be equal and opposite to, okay? Then we know that this here is the adjacent angle, so we can use cos, and cos is equal to the force into the slope divided by 1,000 again, because the weight is 1,000. Go through all the calculations, you get 940 to two significant figures. And so therefore, again, that support force, okay, this one pushing up, must be equal and opposite to that. So again, that must be also equal to 940 newtons. So just to sort of round things off, the wire fence exerts the force in two directions like this. So the net force must be equal and opposite to this one here. Okay, so that one there, the resultant force we worked out before has got double arrows associated with it. We've got closed vector diagram there. Okay, this is the summary, by the way. The calculation involving the forces can be done with trigonometry, so you can use SOHCAHTOA. Yeah, as long as we know what two of those known values, we can work out the third. Objects on slopes can be resolved into their particular components, and that's important that you understand that. Look at the objectives for the overview page for this to see what you need to know. The object is pulling against the surface of the slope and that component there, and it's pulling down the slope in that component there. And because it's at rest, you have equal and opposite forces pushing in the opposite direction. Okay, and we can complete the closed vector diagram by taking this triangle of those component forces and turning it into a closed vector diagram. And I hope you thought that was helpful.